Okay, everyone, we made it to chapter 14. In this chapter, we will have an introduction to linear regression and correlation analysis. So let's check out the learning outcomes for the chapter. In this video, we will learn how to calculate and interpret the correlation between two variables. We will also learn how to determine if the correlation is significant. Then we will focus on how to conduct simple linear regression and how to determine if the regression model is significant. Finally, we will focus on the uses for regression analysis and how to calculate a confidence interval estimate for the regression slope. So if you are ready, let's get started. If you recall way back in the chapter 2.3 video, we learned about scatter diagrams. Before we dive into the topic of correlation, let's revisit that topic now. Recall a scatter plot is a two-dimensional plot showing the values for the joint occurrence of two quantitative variables. We can graph these variables to see if there is a relationship. A dependent or response variable is a variable that we wish to explain. The dependent variable is denoted by the letter y. Then we have an independent variable which is used to explain the variation in the dependent variable. This is denoted by x. So for example, in this scatter plot, we have the x-axis that is the square feet of a house. This variable could explain the price of a house on the y-axis here. If we plot the data, we can look at the scatter plot and observe if there is a relationship between the square feet and house price. So in other words, there is a visual representation of a potential correlation or relationship between these two variables. Let's dive into the topic of correlation in more detail next. When we cannot study an entire population, we use sample data. So that is why we refer to this correlation calculation as the sample correlation coefficient. It is denoted by the lowercase r and is also called the Pearson product moment correlation. Here is the formula, but we will be using Excel to calculate the correlation coefficient. Since we can only eyeball a scatter plot to identify a potential relationship, the correlation coefficient is a way to measure the relationship between the two variables. It is always good to plot your data in a scatter plot to see it visually, but the correlation coefficient tells us more information, specifically the strength of the linear relationship between the two variables. The correlation coefficient ranges between -1 and +1. -1 or +1 indicates a perfect linear relationship. If the correlation coefficient is 0, this indicates no linear relationship. Here are some examples of correlation coefficients with an example scatter plot. So for instance, in this first one where r equals +1, this is a positive linear relationship and is positive because as x gets larger, so does y. When r is -1, this is known as a negative relationship, and again, this is also a perfect linear relationship. We can see all the dots fall on a diagonal line. When x gets bigger, y gets smaller. This third example, we also see a positive relationship, but it's not as perfect as we saw in the first example. So for instance, the correlation coefficient r here would be 0.7. So it's going in a positive direction, but it's not perfect. In this instance, we see a negative relationship where r is -0.55. We can imagine a line here where our dots are going in a particular direction, but it's not perfect like we saw in the second example. In these last two examples here, we can see that both r's are 0. There is no relationship that we could see positive or negative. The data points are all over the place with no pattern. Recall in chapter 7, we learned that the sample data is subject to sampling error. Since we're not studying the entire population, we were just studying a subset. Once we obtain the correlation coefficient using Excel, we must test if it is significant. So let's learn how to do that next. The null and alternative hypotheses are stated like this. This Greek letter here is not P, it's pronounced rho. Rho represents the population correlation coefficient, so when rho equals 0, that means there's no correlation. But if rho doesn't equal 0, that means some correlation exists. If rho turns out to be negative, we have a negative correlation. If rho is positive, then we have a positive correlation. Now, just like in chapter 9, we use the sample data to develop a test statistic for the hypothesis test. We are going to use R, the sample correlation coefficient that we calculated in Excel, along with the sample size to find the t-test statistic. Here is the formula right here, but note that the degrees of freedom for this kind of test is n minus 2. Let's go ahead and do practice problem 14-12. A regional retailer would like to determine if the variation in average monthly store sales can in part be explained by the size of the store measured in square feet. So it seems logical that a bigger store could potentially have more sales monthly because they can carry more products in the store. However, we will run a correlation analysis to see if this is the case, since it's possible the stores are not maximizing their square footage. So a random sample of 21 stores was selected, and the store size and average monthly sales were computed. The data for this problem has been provided in the Chapter 14 Practice Problems Excel file. So the first step you want to do is to identify your dependent and independent variables. Recall that the dependent variable is the variable that we're trying to explain or understand. So in this case, we want to understand the average monthly sales. Then the independent variable is the variable we think might explain the dependent variable. This would be the size of the store in square footage. So in part A, it asks to develop a scatter plot for the two variables and to describe what relationship potentially exists. So here's a scatter plot using the data from the practice problems worksheet. From the scatter plot, it appears that a positive linear relationship exists between the size of the store and the average monthly sales. So in part B, we're asked to compute the correlation coefficient between the store size in square feet and the average monthly sales. So there are a couple of different ways we can calculate the correlation coefficient. The first two options here are using Excel, and then the third option is using StatCrunch. So the first option in Excel is to use the correl function, and you will input the range of the values for the dependent and independent variables in Excel for array 1 and array 2. An array simply means a range of numbers. So the second option is what we'll use for this practice problem. This is using the correlation option within the data analysis toolpack. We have used this previously for running descriptive statistics, but now we will select the correlation option. So on the correlation window, you will want to click on the input range and then highlight the range of data from A1 to B22 in Excel. The data is organized in columns, so you won't change that selection. But be sure to check the labels in first row option. This is because we are including the names of the columns in row 1, so you want Excel to know that, so it does not include the first row in the calculation. If you include row 1, but you don't check this box, you will get an error message that you have non-numeric data. I recommend that you not make any changes to the output options and just let Excel put the output on a new worksheet. This is what the output looks like in Excel. This option is very useful when you need to run a correlation analysis on many different variables, but this is an example of a simple correlation matrix. So the sample correlation coefficient R is 0.8515. Now in part C, we now need to conduct a hypothesis test to determine if a positive correlation exists between store size and average monthly sales. When we are developing our hypothesis test, it is helpful to look for context clues whenever we see words that provide directions such as greater than or less than. In this example, it is tricky because it only says positive correlation, but we know that that is greater than 0. Therefore, the null hypothesis will be that rho or the population correlation is less than or equal to 0, and the alternative hypothesis is that rho is greater than 0. Reminder that the null hypothesis will always have the equality sign in it. This is an upper tail test because we reject the null hypothesis if the test statistic is in the upper tail. The degrees of freedom for this type of hypothesis test is a sample size minus 2. So we were told we had a random sample of 21 stores, so 21 minus 2 is 19 for the degrees of freedom. We were told in the story that the level of significance is 0.025, so that is our alpha. We first need to state the decision rule that we will reject the null hypothesis if the calculated value of the test statistic t is greater than the critical value. So like in the chapter 9 videos, we will use Excel to find the critical value. We will use the t.inv function here and input equals t.inv and then 1 minus 0.025, since this is an upper tail test, and the degrees of freedom of 19, and we get 2.093. Next, we need to calculate the test statistic t. So here is that formula that we saw earlier, and we will just plug in the values and solve. So in the numerator, we have the sample correlation coefficient of 0.8515 that we calculated in part B on the prior slide. Then in the denominator, we will take 1 minus the sample correlation coefficient squared divided by the degrees of freedom of 21 minus 2. We will then take the square root of that whole thing. Then finally, we will divide the numbers and we get 7.08. So our conclusion is, since t of 7.08 is greater than the critical value of 2.093, we reject the null hypothesis and conclude that there is a positive correlation between store size and average monthly sales. Well, that wraps up this first video on scatter plots and correlation. In the next video, we will cover our first topic on linear regression.